Okay, if G is systematic, then H has a nice and simple form. So if G is systematic, G contains an identity submatrix. Without loss of generality, we will assume that the identity submatrix is in the first columns of G. So IK means the identity matrix of order K, because this has K rows and N greater than K columns. So it will contain the identity submatrix here and some other matrix, some other binary matrix, I'll call it P, over there. So P will be of dimension K rows and N minus K columns. So there will be K columns here, must be a total of N, so this must be N minus K. So we want GH transpose to be 0. So if I multiply IKP by H transpose, what I need is that H transpose should be P I N minus K. Why is this? Because if I multiply I by P, I get P. If I multiply P by I get P. Mod 2 is 0. So therefore, H should equal this transpose, which is equal to P transpose. The identity matrix transpose is still itself because it's diagonal. So that's what we have. So if G can be written in this form, then H is this. Now, if G is not systematic, what we can do is we can form any linear combination of the rows of G are still in the code. So I can form a manipulated G, call it G prime, where I do row reduction in order to get an identity submatrix here. So for example, if G, if I start out with 1, 1, 1, 0, 1, 1, this matrix does not contain an identity submatrix. But what I can do is I can do row reduction. I can, basically what I would need is a 0 here, and I can get that by removing that 1 by taking this row and adding it to that row. So I can form G prime. By adding this row to that row, I get 1, 0, 0, 0, 1, 1, and now I have my identity submatrix. H will be the same in both cases because by taking a linear combination of the rows, I don't affect the dual space. Linear combinations of the rows here are still in the original vector space, so I don't affect the dual space. So H will be the same for G and G prime. Now, this trick is not always possible. There do exist matrices where it's not possible to form an identity submatrix like that. Here's an example. In that case, actually no, that does contain an identity submatrix, doesn't it? But more generally, if you sit around and write down pathological examples, you'll eventually find one that doesn't. Actually, here's one. Here's a good one. this does not contain an identity submatrix, and it's impossible to form an identity submatrix by taking by doing row operations, because you'll never be able to get rid of this property that sort of ones are adjacent to each other. You can try it yourself and see, but there's no identity submatrix lurking here. In that case, forming H is still possible, but I just don't want to get into it. In fact, it's not even hard. What you do is you rearrange the columns until you do have an identity submatrix, then you form H, then you de-rearrange the columns, but I don't really want to get into it, so not real hard. But this is the general form over here. So, for example, so let's again take our single parity check. Like so. So, H, so then we have, this is IK, this is P, H is equal to P transpose I n minus K. Firstly, what's n minus K? What are n and K? What's n?
It's 4.
N is 4, K is 3, so n minus K is 1. So what's the identity matrix of order n minus K?
1.
It's just 1, right? So, like so. What's P transpose?
1.
It's all ones, right? So the parity check matrix is all ones. What does that mean? That means that if I take a code word and I multiply it by H transpose, it has to equal 0. What's the property of a code word that would equal 0 when multiplied by H transpose?
Even ones.
It has to have an even number of ones, because I'm adding up all the ones, mod 2, and that's only 0 if there's an even number of ones. Okay. So far we know how to determine whether something is a code word or not. If, actually, excuse me, I'm getting ahead of myself. Suppose C is a code word of an MK code. C is transmitted over a noisy channel. And then Y is observed. Y, which is n 0, 1 to the n. In other words, Y is a 1 by n vector, binary vector, is observed. If that's true, if Y is not equal to C, and even if Y is equal to C, actually, so let me just get rid of that specification. Whatever Y is with respect to C, there exists a vector E in 0, 1 to the n, such that Y is equal to C plus E.